All right, so today we're going to be looking at section 4.1, simple rational functions. The rational function itself is what we're going to be looking at, and we're going to start with the simple ones. So, what is a rational function? Well, a rational function is a function of this form right here, where the top numerator and the denominator are polynomial functions. The bottom one, since it's in the bottom of a fraction, it cannot equal to 0. So, if I have a function that looks like a fraction, then that is a possible rational function. Okay. The domain of the rational function is the set of all real numbers except for the zeros in the denominator. So whatever numbers make the denominator equal to a 0 would not be included in the domain of this function. It means you cannot have it. So we're going to look at the main parent function for rational functions, especially the simple rational functions. It is this function, 1 over x. It is also sometimes called the reciprocal function. And we're going to graph it to see its characteristics and look at it and talk about its domain and range and all that kind of stuff. So I made a table real quickly. I just plug in these numbers up here at the top. Notice that at 0, I can't plug in 0 in the bottom because it would be undefined. So that's what that U here means it's undefined. And we want to see what that looks like in part of our graph. That's an important part. Just plug in the rest of the numbers. You got these values right here. And so let's graph these things. So if I graph this table, I'll get 2 branches of this graph. I'll get this curve looking right here, and I'll get another curve, part of it branch over here, based off of these values. And so when you'll notice that there are some breaks in this graph. So where do these breaks occur? And how do they manifest, and how do I display them? Well, this part up here where we talked about, where I plugged in the 0 and I got it undefined, these are special locations because they become what are called vertical asymptotes. A vertical asymptote is a boundary line for the graph, and it is a hard boundary. That means the graph can never cross this boundary. And you'll notice a lot of times for your vertical asymptotes, what's going to happen is the graph will bend upwards to positive infinity, or it will bend downwards to negative infinity. You can even have them both going up to positive infinity or both going to negative infinity. So that is what a vertical asymptote does. It is a value that is not part of the domain. So if you look at my domain over here, the domain is all the real numbers, and that's what that symbol here means, all real numbers. And you can write it yourself by simply using a fancy R that looks like this. A double line and then a capital R. This means the same thing as that. It means the phrase all real numbers. So all the real numbers, x cannot equal 0, is my domain. Because I can plug in any number I want. There is no other value on the x-axis. So if I run my pencil across it for domains, I run my pencil across it, every x value will have a y value associated with the graph, except for 0. And then as soon as I come off of 0, then I'll stop having a value again, even though I don't see it up there. It is there. So what is this range? Well, range is the same concept here, but only for the y values. So if I run my pencil up and down the y-axis, do I always get a piece of the graph there? Remember, this continue on forever. So at this -3, yep, there's some graph. At -2, yep. Even though I don't see -10, I know this line goes down forever, so eventually it's going to hit at -10. So there's every y value moving up the y-axis, except at 0 in this particular example. And the moment I come off of 0, then I'm going to start picking up values again. So this is called an end behavior asymptote. It is not the same as a vertical. An end behavior asymptote is referring to what happens on the ends in a simple rational function. In this particular case, it's a horizontal asymptote, and it is a value that the graph will get closer to. Okay? It happens out here at the ends. So when you look at the end behavior asymptote, why does it say y equals 0? It's a dotted line. The graph is if I go out farther. So if I plug in a number like 1,000,000 into this equation, I'm going to get 1 over 1,000,000. That's a very small number. In fact, it's really small. It's very, very close to 0. And so the end behavior is basically telling you, when I go to the extreme ends, way out there at 1,000,000, 1,000,000,000, the graph is going to take on the characteristics of this end behavior asymptote. Okay, that's what it does. Same thing on this side. If I plug in a -1,000,000,000, the number is going to be so close to 0 that it actually looks like 0. And so that's how the end behaviors work. In a simple rational function, it is a horizontal. In later rational functions we're going to talk about next time, we're going to change what this end behavior looks like. It can be any end behavior, any polynomial, anything really. But in our particular cases, it's going to be a horizontal line or it'll be a diagonal line. We're not going to go beyond that. So remember, horizontal asymptotes are also mainly called end behavior asymptotes. Horizontal is because it's a special case. And so in this case, the difference between a horizontal asymptote and a vertical asymptote in the sense of what the graph does to it, the vertical is a boundary line that you can never cross. A horizontal line only cares about what happens at the extreme ends, meaning I can cross it. So just because I have a horizontal asymptote does not mean I can't cross it. For example, there are graphs that do stuff like this. Let's say I have a horizontal asymptote right here, okay? And then there's graphs that do this. And they go back and forth, and as I go farther and farther out, it gets closer and closer to 0. And so eventually it's so close that it basically bounces back and forth. And so what happens is way out there, it still looks like 0. But notice how many times I can cross it. So you can cross horizontal asymptotes or end behavior asymptotes. You cannot cross vertical asymptotes. So the simple rational function form, and we're going to be looking at through the lens of transformations also, is this right here. So here's what a simple rational function looks like so. It's in transformational form. The numbers down here on the bottom is what's considered to be in parentheses. And this is associated with your right or left transformations, your horizontal transformations. So that's going to deal with the vertical asymptote, because as I move a graph right or left, so moves the vertical asymptote. This number out here is your horizontal asymptote, because this also means up and down. And so again, the up and down movement changes where the horizontal asymptote is going to be. The number on top up here is where your reflections or vertical stretches or shrinks. Okay? And so we're going to look at transformations to help us graph some things out and other things. So how do I graph a simple rational function, which is what it'll be required of you to do. So here's what you should do, and I'll show you an example here in just a moment. So the first thing you want to do is you want to take the denominator, you want to set it equal to 0 and solve it. When I do, I'm going to get the vertical asymptote. In this particular case, x equals h. It also tells me my right or left transformation. The reason why you want to do this is because even though this one is not showing that there is a number in front of x, there can be a number in front of the x. Okay? And so with that in mind, that number is not necessarily going to be the vertical asymptote. So if you do this, you'll get the vertical asymptote and your right or left transformation. Next is you want to determine any end behavior asymptote if you have it. In this particular case, it's very simple to see what that would be. It is simply whatever the number is being added or subtracted. And so if there is no number, then it's going to be at y equals 0 like this one up here. Then we're going to make a table, and we're going to center the table around your vertical asymptote. Wherever the vertical asymptote is, we're going to pick a couple numbers to the right and a couple numbers to the left. When I have all that, I'm going to graph the asymptotes first as dotted lines. Then I'm going to label them like I did up here. I'm going to name them. This is y equals 0. This is x equals 0. Then we're going to graph the points from our table. Then we're going to draw the curve and label 1 point on each branch. And then we're going to identify the domain and range. And so we're going to do that with this example that I have ready to go over here. We're going to graph that function right there. Okay? So the first thing we want to do is we can take this denominator. We can set it equal to 0. And then we move and solve this for x. And so x equals 3. And that tells me several things. First off, that is my vertical asymptote. You want to write your vertical asymptotes as an equation, not a number. We write it as x equals, and the horizontal would be y equals. The transformation over here says it's positive. We're going to the right 3 units. The next thing is we'll look over here at our number being added or subtracted on the end. It is a +2. That means we're going to move it up 2. So this is up 2 units. And that number is also going to be my horizontal asymptote, y equals 2. Make sure you put it as an equation, y equals 2. Take the vertical asymptote, put it into our table in the middle. We know that's going to be undefined there. And this gives me a place to put 2 numbers above and 2 numbers below. So if I have 2 numbers above, just pick the next 2 numbers. 2 numbers below, just pick the next 2 numbers. And because we have 0 is the y-intercept, sometimes you might want to put in the y-intercept. It's very useful to have. It's one of the major key points of things. Once I have this, then I just take these numbers and I plug it in here. Don't worry about, any kind of fancy way of doing the fractions and stuff like that. Just keep the fraction. If I plug in a 4, I'm going to get 4 minus 3, which is 1. 1 divided by 1 is 1. 1 plus 2 is 3. If I plug in 5, the bottom is going to become a 2. So this is 1/2 plus 2. 1/2 plus 2 is 2 1/2. There you go. If I plug in a 2 in here, 2 minus 3 is -1, so this becomes -1. -1 plus 2 is +1. If I plug in a 1, I'll get -2, so this is going to be a -1/2. And if I take a half from 2, I get 1 1/2. If I plug in 0, this becomes a -1/3. And if I take a third from 2, I get 1 2/3. See, just leave it as the fraction, keep it simple, don't overwork it. All right, so once I have my table with some values in it, I am ready to start graphing and laying this out. So you're going to graph the vertical and horizontal asymptotes first as dotted lines and label. So we have a vertical asymptote at 3. So we're going to put a dotted line at 3. So be careful here. Make sure that you make it long enough that it goes the same size as your axes. So there's my dotted line. This is x equals 3. Then we'll do 1 and 2 for the horizontal. Label that, y equals 2. And what it does is it shows you that you have these 4 little areas that the graph is going to land in. And the table is going to tell you where those are going to be. If I graph 4, 4, 3, and I put a dot, I know that one of the branches is going to be right here. And then at 5, we have 2 1/2, which is right here. And that is enough to actually draw this curve. So if you look at it, what the curve is going to do, we have to get closer the farther out I go this way, and we got to get closer as I get to that one. So it's going to bend all of these. So just hug this line. As you get closer to the dot, start curving up. And then curve it nice and smooth and get closer to that line. Draw arrows on the end. That branch is drawn. And then you label a point on that branch, usually the one that gives me a whole number, if I have one. Most of the time, it's be the number right after the vertical asymptote, but not always. Over here, graph these things. So I have 2, 1. And then 1 is 1 1/2. 0 is 1 2/3. So you can see there's my dots there. Same thing. Hug this line. Start curving it as I get closer to the dots. Make it go nice and steep in that direction. Arrows on the end. That branch is done. Label a point. And that graph right there is complete. That's all you have to do. Okay? So what is my domain? Because this is a simple one, it's fairly simple to see what it's going to be. It is all the real numbers, comma, x cannot equal 3. And the range is pretty obvious too. It is all the real numbers. The y cannot equal 2. And there's how you draw the graph, label it, and identify the domain and the range. Okay. The next problem I want to look at is a application problem down here at the bottom. We're going to do a car purchase. We have car A and car B. Here's the purchase price of these cars. This is the monthly expense for operating each of these cars. Gas, maintenance, all rolled into one kind of amount. And what we want to do first is we want to write a function that represents the average monthly cost, which we'll call C of X, of owning each car, where X represents the number of months that you've owned the car. So the word here, average, is what you would normally think. So average means we're going to add a bunch of stuff up, and then we're going to divide by how many things I added up. Okay? And so that's how we're going to do this. And we need to write some rules for this. And so before I can write the rule, I should probably practice and see if I can figure out a pattern for how this works. So keep in mind what average means. It will help us out. So we're going to come over here to this. I have this set up here. So we got the C of X is the average monthly cost of the car. X is the number of months that you own the car. And the 0 month here is basically the start value. So car A, little sub A, little sub B here. Car A was $4,999, and this one was $3,499. Okay? So what's going on? So what is the cost of this car? Well, this car, I'm going to add, every month I'm going to add basically $150. So if I take this number right here, and I add $150 to it, let me get my calculator up and run here, get these values for us. So if I take this thing here, $499, and I add $150 to it, then I get the next value, which is $5,149. And since I added $150 to this, take this number right here and divide by 1 will give me the average monthly cost, which is this right here. Okay? Let me get my paper. So the next time I'm going to add, the next month, I'm going to add another 150. I'm going to add 150 to the previous answer. Okay? So 5149 plus 150. Okay? And if I do that, then I get 5,299. But this is the second month, so this is the second time I've added 150, so I need to divide that by 2. And if I divide that by 2, I'm going to get 1,324. I'm just going to do the whole number portion. Okay? About that right there. So that's what's happening. Well, what am I going to do next? Well, I'm going to add 150 to that. Okay? And so forth and so on. Each and every time. So how do I write a rule from this if I keep doing this? Okay? What's the rule that's occurring? And I can go through and find all these values, and we're going to, but I'm going to show you another way to do it. Once I understand how this pattern works, everything is based off of the original cost. So I started with $4,999. And to this, I'm going to add, so if I want to go up to 10, what do I have to do? Well, I have to add 150 10 times. So I'm going to add 150 10 times. Well, that means I added 10 150s. So the average means I have to divide by 10. Okay? So that's how this works. So if I do a 20, then this number becomes a 20, and that number becomes a 20. So this is the pattern that's emerging. And so we can find our rule based off of this by simply putting in our X. So the cost of car A, our monthly cost of car A, the average monthly cost is $4,999 plus 150 times the number of months divided by the number of months. And then C of B, then, the average cost for car B is very similar in nature. This one started at $3,499, and its a monthly cost is $185 times the number of months I did it, divided by the number of months I did it. So there we get two equations that are very similar in nature. And they are rational functions because they have a polynomial on top and a polynomial on the bottom. So a problem problem like this, real life problems like this, once you have a pattern and a rule that you can follow, you can then use the calculator and graph it and see what it looks like. And so I have done that for you. I want you to see how this works. So here it is over here in this one. And so I have graphed it, and there's the two graphs. This graph right here on the top is the f of 2, which will be equivalent to our c of a. And the one down here is the one c of b, the b card. And so you're looking at these graphs, and you can see that they look very similar, but something special happens right about here. Okay? So before I get back to this, I want to help you how you can use the calculator to help you fill in the rest of this table, because I don't want to have to do it all by hand. We're going to use the calculator to figure this out for us, and it should be hopefully a reminder for you, or a refresher, of course. You push the menu, and then you go to trace, number 5, and you're going to trace the graph. Down here, it tells me I'm on function 2, which is CA, this one right here, and it gives me a value. So what it shows me right here is that at month 45, that is the average cost right there, $261. So we can then type in any number I want. So like over here, I can type in the 2, and then I can hit enter, and it will tell me the Y value for the 2. And somehow I have the wrong number. I know what I did. But anyway, let's go to 3, and we'll enter in these numbers. I'm on the wrong graph, that's why. I don't know what happened there. This is 1816. And let's go to 5. And this is 1149. Let's go to 10. So all I'm doing is just typing in these values and letting the calculator do the work for me. 649, 20. This is 400, 30. This is 316. And then 40 is 274, and then I can do 90. And the reason I'm doing this table is because it will help me in drawing the graph that you saw on the calculator. That one's 205. And then I can go to the next graph, and I can start typing in these numbers. 223. This is 272 and 301. And you can see how much faster this goes. This is 360. So the trace feature is what you want to look for. 884, 1351, and this is 1934. Okay, and so that gives me my table. And let's do 10. I'm just trying to get my graph back to where it was so you can see it. So again, we want to produce that picture in our graph so we can see where things are occurring. So that's why we made the table of values. And we just simply go ahead and graph these things very quickly. My scale down here is at 10. You won't be able to see the chart because it's too far off the page. But at 10, we're going to graph the first one. We'll graph this one real quick. At 10, we got 650. So 650 at 10 is about there. And then at 20, we got 400. And at 30, we're at 316, so that's about here. At 40 is 274, which is about there. And at 90, so we have a wide range out here that makes it a little bit easier to draw a nice smooth curve. We're at 205, which is just above the 200 there. And so then what I want to do is, now I'm not sure exactly how far this goes out here. We'll talk about that a little bit later. But these dots are a nice smooth curve. You saw it. It is the one branch. So just draw a nice smooth curve through these things. Go up through that point and kind of head up towards the top and just kind of extend this one out in the same fashion. We don't know exactly where it's going to go, but we will explore that in a minute. So this is your CA, car A. So then we can do the same thing for car B, put some dots in there. Starting at 10, we got 535. So here's 550, 535 is about right here. And then 20 is 360. So 360 is about here. At 30, we got 300, so just below that one. At 40, we're at 272. This is at 275. I mean, these are almost on top of each other right here. That's an interesting little value. At 90, we're at 223. So this is 250, 223 is about right here. So you see now this one is now above the other one. So this graph is going to come from here. It's going to go through, it's going to come over here to this point and curve up through those dots. And this is car B. And so when something's interesting happens right there, and you'll notice that this is some of the questions that they're going to ask you in this problem. So once we have a graph drawn over here, we're going to still use the calculator to answer some of these questions. Is the average monthly cost of owning each car ever the same? Justify your response. Well, I can see from my picture that yes, indeed, they are, because they switched places. Car A was on top, then car B was below it. Then at some point here, it switched because now car B is above car A in cost. So where does that occur? On the calculator, we can calculate that fairly easily. Get this glare out of here somehow. So do it on the calculator, menu, 6, analyze the graph, and you'll see number 4 says intersection. So this is how I can solve equations to see where things cross. So you remember when you did in Algebra 1, you did systems of equations, finding where they cross. Well, this is the same thing. These two graphs cross, so where do they cross at? So this little dotted line with the fingers pointing here, you want to go to the left of where you think it crosses at. That's the lower bound. You don't have to be right next to it. It's somewhere to the left of it. You hit enter or select. Notice it says now upper bound. Slide it across, and a dot is going to appear. Select that. And so this is where they cross at month 42.857, or basically the 42nd month. And this is the value that it becomes, $266. So the answer to their question is the average monthly cost of owning this car ever the same? And the answer is yes, they are. In the 42nd month, they both have an average monthly cost of approximately $266.64. So that's how you would answer it with a complete sentence using their information to answer the question that they asked. The next question is, when does the average monthly cost of owning car A reach $160? Is this a reasonable answer? Okay, so if I look at this trace feature that I had before, at 42, it's 266. So I need to go out farther to see if I can get that number here to be less than 266. So I'm going to go to the menu. I'm going to go to the trace feature, and I'm going to start plugging in numbers until I get this number out here a little bit farther. So at 42, it was 266. Let's do, I don't know, let's just do 100. At 100, it's at 199. Well, I got to go farther. Well, what's it at 150? That's only 183. I still got to go a little bit more, don't I? So let's put in a bigger number. Let's put in 300. Let's double that. Well, now I'm at 166. Well, I'm getting closer, right? Well, let's just do 350. What happened? Well, that only went down even a little bit. So I got to go even more. So what's 450? No, I'm closer. 161 at 450. there's 500. At 500, I'm at 159.99.8. So that's basically $160 right there. So that tells me that in month 500, when does the average monthly cost to own a car reach $160? Car A will equal $160 in month 500. Is that reasonable? Well, if that's 500 months, how many years is that? How many years is 500 months? Well, take 500 and divide it by 12 because it's 12 months in a year. And what you're going to find out is it's basically 42 years. Or 42 years. Is that a reasonable answer? In my opinion, no. Because this is a used car, 42 years is very unlikely for the car to survive that long. Some cars last that long that are used, but highly unlikely that an average car that you pick up at Loan a Car Fresno is going to be lasting for 42 years. So I don't think this is a reasonable answer because of that. And so you would write that sentence to that. So I would say no, because 500 months is about 42 years, and most cars do not last that long. So that's how I would answer question number 4. Question number 5. What is the least amount the average monthly cost of owning car B can ever be? This question is literally asking you, what is the end behavior? So what is the least amount it can ever be? Well, we saw that this car reached 160 in 500 months, but is that the lowest it can be? So what is the lowest car B can be? So if I go out here farther and farther, well, let's look at the equation of this, and you'll see how I can find the answer just by looking at the equation. Okay? And so it's all about the number I pick. So if I have a number that's out there very, very far, I mean, 500 is far, but it's not far enough. Let's go out there even farther, and let's look at the equation to help us figure out these numbers. So I'm going to type this in a fraction form. So 3499 plus 185 times a number. Let me put it this way, delete that. Put a parenthesis, and I'm going to put 1,000 just for a placeholder. And I'm going to put 1,000 down here, so you can't see it. So if I do that and I look at an answer, it's $188. Okay, that's pretty low. Can I do more? Well, I'm going to change that 1,000. I'm going to add 3 more zeros. Oops, those aren't zeros. And then I'm going to add 3 more zeros down here. So that's now 1,000,000. Look what's happening. Okay, so what's happening is this number gets so large. Okay, that's 1,000,000,000. See how the 185 is staying and all this other part's getting smaller and smaller and smaller? Look at that number right there. What is that number? Well, that number is that number right there, isn't it? What's happening is this is getting so large, it's 185 times this number, is so large that this number over here, this 3,499, is like nothing to it. It's insignificant. And so literally it's like not being there. So the farthest I can go would be whatever this becomes. And that's the smallest it can ever be, would be the $185. That's the smallest it can ever be. So the 185 is what's considered to be an end behavior asymptote, a horizontal asymptote. And in fact, if you look at the graph of this thing, you can actually come down here at 185, which is right about here, and you can draw the horizontal asymptote across there. And you can see that these lines are going to get closer and closer to it as I go out farther and farther and farther. So it is a horizontal asymptote for this graph. Okay, and so that's how this works. And we'll do some more graphing, which is the main part of this. And some of the word problems we're going to be doing are going to require you to draw pictures like this from a table. A lot of times dealing with geometric shapes, areas, and perimeters. But we'll talk about those together in class. So that ends this video.